Yes, my name is Gaudio. I'm going to present you our paper, a lightweight messaging engine for decentralized data processing in the Internet of Things. As a use case scenario, we have a conveyor belt scenario with multiple sensors and actuators, and a conveyor belt that transports products between different productionist machines. So we have a distance sensor which measures whether the item is placed correctly on the conveyor belt, an item relocator which that places the item to the correct position, an RFID reader that reads RFID information from the product, a camera that takes a picture of it to evaluate whether it's in a perfect condition. And then depending on the information, the conveyor controller sets the turnouts correctly for each specific item. And typically, you would collect the data from the sensors, send it to a cloud infrastructure or some distant infrastructure where, in order to be processed, and then the result back to the IoT environment to control the actuators. And our idea was to get rid of this communication overhead and send data directly from devices between the devices and process data directly on devices. So this data processing has several benefits. For example, we have less communication overhead. We have scalability, since with each new device that enters the IoT environment, there comes new processing power and no or not that much communication overhead. We're utilizing devices' computing resources, so we don't have to buy cloud infrastructure or something. And it's also privacy enhancing, since data does not have to leave the IoT environment. But there are also some challenges. We need lightweight software solutions whose devices are more constrained than big servers. We need dynamic environments, which means devices need to be able to handle failures or new devices themselves. Devices need to be autonomous in terms of self-controlled, and the utilization of multiple heterogeneous hardware is also a challenge, since same software must run on different hardware. To tackle at least some of these challenges, we developed a lifecycle method with 5 steps. First, the data flow model needs to be modeled. In a second, I'm going to tell how this looks like. Then we need to create the network topology, which means that we have to define which devices are part of our environment. Then we can execute the data flow. Maybe a device fails or is intentionally removed, or a new device enters the environment. Then the network topology is modified, and eventually the data flow will be retired. So the data flow model, this is an example for the conveyor belt scenario. It only shows the abstract operations and the connections between them, and not the actual data that is transmitted. So we first get the position of the item, then we can parallelly check the position, read the RFID information, make a picture, maybe relocate the item, and then compute the path based on the information and set the turnouts accordingly. So with the data flow model, now we need our network topology. So these are our 3 IoT devices and the conveyor controller, which are all connected via some local area network. And then we have to map the operations onto the IoT environment. So IoT device 1 checks the position, or gets the position information, since it has the distance sensor, then it can directly check the position and maybe relocate the item by controlling the item relocator. The RFID tag is read by IoT device 2, IoT device 3 takes the picture, and then the conveyor controller can complete the path and set the turn on accordingly. So we have data flow model and the network topology, and now the data flow can be executed. In order to do this, devices need to be able to autonomously exchange information. And to achieve this, we created a messaging engine architecture, which is basically the main part of our paper. On the top, we have an IoT device with a messaging engine as a black box. And in the middle, we have an IoT device with a messaging engine and all its components. So data is packed into messages to be sent between devices. They are received via the message consumer. Message consumer puts them into a queue. When the device is ready to process a new message, it takes the next message out of the queue, looks into the data flow model, which operation needs to be performed on the message. Then the application wrapper knows which exact application to call in order to perform the operation on the device, and then the result is packed into a new message, put in an outgoing message queue, and then sent to the next device according to the network topology and the data flow model. We implemented our solution using the constraint application protocol for communication, which is basically a lightweight HTTP, implemented in Python, used a small database for message queues and model storage, and we had a testing environment with some Raspberry Pis and virtual machines. To evaluate our solution, we wanted to compare the overhead of the messaging engine to a central solution with a process engine. And in order to achieve this, we measured the time between receiving, processing and replying a message, and compared the overhead to a simple HTTP script, which would be the device part of a central solution. And yeah, now this overhead must be compared to the overhead a process engine takes, and also the communication overhead between the devices and the process engine. And the mean overhead of our messaging engine was 0.68 seconds, which now it should be compared to the overhead of the process engine. So as a conclusion, I want to shortly look at the challenges I listed in the beginning. We have a lightweight solution. We have mechanisms to create a dynamic environment to handle failing devices or to integrate new devices into the environment. Devices are more self-controlled by our solution, but not completely. And heterogeneous hardware may be tackled by us in the future. Thank you very much.
So as we don't have problems to change to the next one, we will have some time for questions. Nobody has questions here, Philip? I have. Maybe I skip the last session. The scalability, when I have a situation where I have a very large number of these basic IoT devices and they have a really dense communication pattern. So everybody has to talk to almost everybody. Compared then to the centralized solution. It's think about different kinds of different kinds of scenarios or graphs of communications between the IoT devices, because everything goes through the IoT device, and sometimes you can't reach an IoT device without going through three others. Maybe it's a more widespread application or something. You thought about these things? Because the reachability of messages in a bigger IoT scenario is not always that everybody can reach every other device directly.
Yeah, this is this constraint should be modeled in the network topology, and then devices should the data flow model should be in such a way that devices propagate the messages.
So you would put in propagating nodes or nodes as a role as IoT device as well as propagating nodes, right?
Yes.
Okay. More questions? No. Then to the next one.